A regional hospital spent 16 months and $3 million building a machine learning model that predicts sepsis on set 4 hours before clinical presentation. The model is genuinely impressive. In validation, it outperforms every existing early warning score in the literature. The clinical informatics team presents the results to the CMO. Deployment begins across 3 pilot units. 8 months later, the program is suspended. The model never failed. The Joint Commission review did. Auditors asked the program office to demonstrate how the system produced a specific prediction for a specific patient at a specific moment. The system could not. The feature pipeline pulled from 17 data sources with different update frequencies, different terminology standards, and different provenance records. Nobody had built the layer that connected model outputs to verifiable clinical assertions an auditor couldn't trace, validate, and sign off on. The model was right. The system was unauditable. In a regulated clinical environment, these are not separate problems. They are the same problem. $3 million and 16 months later, the program office learned that lesson. This is where good models go to die. Why machine learning ROI fails before the technology does. ML Part 30. Why a clinically accurate model and a failed deployment are not contradictions, and what the ROI calculation missed before the first line of code was written. Section 1. The value assumption problem. Every machine learning project begins with a theory about where the value will come from. Those theories are frequently wrong in ways that only become visible after significant investment. The most common version is solving a problem that is not actually a bottleneck. The customer service team builds a ticket classification system that routes inquiries to the right specialists automatically. The model classifies accurately, but misrouted tickets were never the constraint. Response times were slow because specialists were overloaded regardless of which queue the tickets arrived from. The model solved the routing problem with the precision and delivered zero business value because routing was never what needed solving. 6 months of model development produced a technically successful system addressing the wrong question. A subtler version is overestimating the financial impact of genuine improvements. A fraud detection model catches 15% more fraud than the previous rule-based system. The business case projected proportional reduction in fraud losses. Post-deployment analysis revealed that the additionally caught fraud in small amounts where recovery costs exceeded the value recovered. The model improvement was real, the financial impact was not. The business case had assumed that more fraud caught meant more value recovered without examining whether the marginal fraud was worth catching. The most expensive version is underestimating available alternatives. An inventory optimization system promised better stock positioning through machine learning. After deployment, analysis showed that increasing safety stock by 10% across the board delivered 80% of the benefits at 5% of the cost. The machine learning system was technically superior and economically unjustifiable. Section 2, the implementation cost problem. Machine learning projects get approved on budgets that count the model and omit the system. The data engineering infrastructure required to feed production models reliably costs as much as the model development itself and appears nowhere in most initial product approvals. Feature stores, data quality monitoring, pipeline orchestration, and the labeling infrastructure recovered in Part 11 were not optional additions. They are prerequisites for production operation that gets discovered after approval when the budget is already committed. Operational overhead is the cost that kills programs in their second year. Maintaining production machine learning requires a permanent ongoing investment in monitoring model performance, investigating accuracy degradation, coordinating retraining schedules, and managing the data quality failure that surface continually in real organization environments. Organization budget for building the model. They do not budget for permanent team required to keep it working. When those costs surface in year 2, ROI calculations that looked sound at approval time flip negative against a system that is now embedded in operational workflows and expensive to remove. Integration complexity is what the sepsis model program discovered. Connecting machine learning outputs to existing business processes, enterprise systems, clinical workflows, and audit requirements surface assumptions that were never examined during development. The integration work that gets estimated in days takes months. The semantic mismatches between what the model produces and what downstream systems expect require resolution layers that were never scoped. By the time integration complexity is fully understood, the program is too far committed to redesign. Section 3, the semantic interoperability failure. This is the failure mode that the standard ROI framework does not capture, and that regulated domains surface most brutally. The sepsis model pulled features from 17 data sources. Each source used different terminology for the same clinical concepts. Creatine levels appeared under different field names with different unit conventions across laboratory systems. Medical records used different drug classification schemes across pharmacy systems. The model learned to navigate this inconsistency during training because the training pipeline normalized it invisibly. Production deployment revealed that the normalization was brittle, undocumented, and untraceable. When the Joint Commission asked which data source contributed to a specific prediction, the answer required reconstructing a feature pipeline that had never been designed for reconstruction. When auditors asked whether the terminology used in model features matched the terminology in clinical ontologies governing hospital automation standards, nobody could answer because nobody had built the connection between model features and the formal clinical definitions. As we covered in parts 15 through 23, the semantic layer is not a reporting feature added after the system is built. It is the infrastructure that makes model outputs traceable to formal knowledge representations that auditors, regulators, and clinical governance bodies can independently verify. A machine learning system operating in a regulated domain without semantic grounding is not a complete system awaiting final polish. It is a system with a structural gap that will surface at the worst possible moment, which is always during the review that determines whether the program continues. Section 4, the adoption barrier problem. Technical success means nothing if the people who need to act on predictions don't use them. Workflow disruption is the most predictable adoption failure and the least planned for. Machine learning predictions require changing how people work. Clinicians must check early warning scores before rounds. Loan officers must incorporate model recommendations into decisions. Warehouse managers must trust demand forecasts over intuition built across years of operational experience. Each workflow change creates resistance that project plans consistently underestimate. When adoption is optional, people revert to familiar methods, and the machine learning system runs in production, generating predictions that nobody acts upon. Trust deficits compound workflow resistance. Users do not trust predictions they cannot interrogate. A sepsis early warning that fires without explanation forces a clinician to choose between acting on an alert they cannot evaluate and ignoring a system the hospital spent $3 million deploying. Without explainability that connects predictions to clinical reasoning, clinicians default to their own judgment. The model becomes a background process that generates alerts nobody believes. Performance gaps in the cases users notice destroy confidence in aggregate accuracy that users never see. A recommendation engine that performs well across the full customer base but poorly for the high-value accounts that sales teams focus gets written off entirely. Cherry-picked failures from demonstrated aggregate performance. The model that is right 80% of the time is remembered for the 20% that was wrong. Section 5. The measurement problem. Organizations consistently measure machine learning success using metrics that do not connect to business value. Model accuracy, pipeline uptime, inference latency, and deployment velocity are the metrics that data science teams can produce and leadership can understand. None of them answer whether the business is better off. A model at 95% accuracy that nobody uses delivers zero value regardless of technical excellence. A pipeline running at 99.9% uptime powering predictions that do not change outcomes is infrastructure spending with no return. Proxy metrics extend this problem into the business reporting layer. Business case built around improved prediction accuracy rather than improved business outcomes create the condition for the pattern that kills machine learning programs. The data science team reports success. The business reports no improvement. Both are telling the truth about different things. The gap between those two truths is where programs get restructured. Section 6, why this matters. The sepsis model program failed on every dimensional simultaneously. The value assumption held, early sepsis detection generally improves outcomes, but the measurement framework never connected model accuracy to patient outcomes, to financial input in a chain that the CMO could defend to the board. Implementation costs were underestimated because the semantic infrastructure required for audit compliance was never scoped. Adoption was undermined because clinicians could not interrogate predictions, and the audit failure that suspended the program was visible in the architecture from the first sprint if anyone had asked whether the system could trace its outputs to verifiable clinical assertions. None of these failures required bad decisions to occur. They required the standard project approvals and execution framework applied to a domain where that framework is insufficient. Machine learning projects that deliver sustained ROI in regulated environments are not smarter about models. They are more honest about the full system the domain requires before the first model is trained. In part 31, we learn about machine learning governance and why it differs fundamentally from language model governance, and why the semantic layer creates a third governance domain that neither framework currently addresses.